Alright, hi. So in today's video, I want to run through a question, and this is to do with tension design. So if you imagine two cases, right? So let's call it scenario, well, it's called case 1 and case 2. First we have a PFC, which is like a bracket-shaped member, and it's connected, it's bolted to an equal angle, okay? Which is like an L-shaped member. And that's the cross-section that you just saw. And here's the actual kind of longitudinal direction where we have tension pulling it on both sides. Kind of like if you imagine a link of chains, we have it's being pulled in tension, right? Or in this case, it's called N star. You can also call it N star T, whatever. So if you imagine, just continuing the chain analogy, if you imagine that one of the chains breaks, the whole system fails. So essentially that's what we're going to be checking in tension design, right? We're checking essentially the weakest link. And if you think of these chains as different failure modes, right? Some of them could have less cross-sectional area, which could be one factor, and another thing is they could have different strengths. So for example, you know, if this one is Fy is 380 MPa or something, for example, this one, we're looking at fast fracture, so it's Fu times 0.85, where Fu is like 480 or whatever. Anyway, they could have different cross-sectional areas and they could have different strengths, okay? So we have to check all of them, see which one fails first. Okay, so that's the general approach that we're going to do. Let's focus on case 1, which is this top case here. So what is actually going on here? So it takes a second to digest, and I would recommend looking at the right-hand side first. So we have a PFC, which is, we have an equal angle behind here. Let's do that dashed lines. And it's behind the PFC that we're looking at, okay? It might not be immediately obvious to you, but if you consider dashed lines as lines which represent something that's behind something else, right? So in front of us is the bracket. Let's do it in, I think I did it in green before. I'll do it in green. Okay, so that's in front of us, right? That's the top and the bottom flange of the PFC. And yeah, behind we have the dashed lines for our equal angle. Okay. We have this series of bolts, right? And they can fail. The bolts will affect the fast fracture failure mode. But let's check the yielding first. So that's the setup. And let me just clarify which thing is which. So on the left here, the PFC is that one. And this is the equal angle, okay? For reference, the 380 in front of the PFC refers to its depth, right? So when you're drawing it, that's going to be 380 deep, right? And 200 by 200 means each leg, we call these legs, is 200. So that's 200 and that's 200. And that 16 there is referring to it's 16 millimeters thick. So that dimension is 16 thick, okay? All right. So first, we have to pull data from One Steel, right? So if you go to Google and you type One Steel catalog, you basically, well, I've already downloaded it, but you get a PDF and it looks like this, and it's for hot rolled structural steel products. So hot rolled is just like a type of manufacturing process, and it's going to be all your PFCs, your I-beams, your equal angles, and your unequal angles, etc. The ones which won't be on here are like your rectangular, let me draw on here, oops, just a bit slow. Rectangular hollow sections won't be on here, circular hollow sections won't be on here. Yeah, the rectangular and square hollow sections, I should say. These ones. So these will be on a different document. But anyway, so if we go down to equal angles, for example, right? It's on page 23, and we want to look at 200 by 200 by 16, okay? So here we are. This one. All right. So we want to grab a few parameters from here. The first one is your area, right, which is 6,200. The thickness, right, which is 16, as per the name. And what else? And also, if we scroll down right to the next page, we get, okay, so basically the difference between this table and the one on the next page is this table is geometric properties only, right? If we want material properties like yield strength, we want to go to this next page. And we're told that our question is, sorry, let me go back to the question real quick. Okay, I forgot to mention this part. We have, it says that all the plates are grade 300, but the plate here, I'm running out of colors. Plates, I'll do in purple. The plate, which is the flat plate here, is in case 2. So we'll ignore that for now. But what it is saying is that the equal angles and PFCs are grade 350, okay? So that's gonna help us check on one steel. So we go back to one steel and we go to grade 350 over here. Again, we're looking for the 16 thick 200 by 200 equal angle, and we can see its yield stress here. Yeah, I think that's the only one we need. 340, okay. So if we go back to this, right, 340. Okay, so that's where this comes from and this comes from, and we figured out where the area was from, and if we go to the PFCs, we're going to be able to find the area as well for the 380 PFC. These are from a different table. If you go to my week 1 notes, it's from this table basically, and you can also find the yield stress on this one if you want as well. This column here, tensile strength, right? So we go to grade 350, and we know that the thickness is 16 mil, right? And 16 is between 11 and 40. Let's see if 480 is the tensile strength, which is over here. I'm gonna undo all that because it's my master copy. Cool. Okay, so that's where 340 is from. Happy days. And that one's 16 thick, and if you go to one steel, you can find out that the 380 PFC is 10 thick as well, 10 mil thick. So that's where all our data comes from. So once we have the data to do the question, next, like the easiest thing to check is the yield failure. So we have to check the yield failure based on the gross section, which just has this formula. So we get the gross section area, which is AG, and we multiply it by our yield strength. So, sorry, just bring up my notes. This is 6,400 for the equal angle, and for the PFC, it's 7,030. The yield strength was 340 for both. Right, and that gives us 2,108 kilonewtons and 2,390.2 kilonewtons. Sure, okay. So we'll keep these in mind for later. All right, next we have the fracture on the net section. So this one takes a little bit longer to do because we have a couple of different failure modes. So if you look on the right hand side here, we have the bolt fracture patterns, right? And if you just pause the video and have a think about it, think about how like the 3 combinations of patterns that different combinations of bolt fracture patterns which will result in a different net area. Okay, so the first one looks like this in its unstaggered holes. All right, so we'll call that failure mode 1. The second one will look like this, where we have 3 bolts in the fracture pattern. And the third one looks like this, where we have 4 bolts. So you might be wondering, okay, what about over here, right? We have a different set of 2 bolts. But if you think about it, it's just the gross area minus 2 bolts, just like it is over here. This is the same as failure mode 1 actually. And then you might be thinking, okay, failure mode 2, what if you do that instead? So it crosses across 3 bolts and it has the same diagonal pattern. So therefore it's the same as the other one I drew. So there's only 3 combinations that you're gonna run into, okay? Oh, my leg has pins and needles. Give me 1 sec. I turned off the video for this specific, I turned off my webcam for this specific video because I wanted to be more like Khan Academy. But anyway, you can't see me fidgeting around. Okay. Alright, I've changed how I'm sitting. Okay. And I apologize for the quality of the video. When I'm recording at home, it's a little shitter than if I'm recording at uni, basically. But anyway, just because of how Discord shares things. Okay, so let's talk about the diameter of the holes next, right? So, oh, sorry, that should be pointed here. Okay, so 16. Oh no, that's correct. Okay, sorry. Let me log back in. So basically, 16 is the diameter of the bolt. Okay, because we're told that we have M16 bolts. So it might be 16 thick bolt, okay? But then the bolts, they might look like that. They have these threads, right? And that thread, we can assume is 1 millimeter surrounding the bolt. So we have to subtract 2 mil to account for the 1 mil on either side of the increased diameter from the hole. So that's where the 2 mil comes from. So we have holes, right, which are 18 diameter. Okay, so next we have to figure out what KT is. Okay, so let me explain it short. Let me explain the short version, and then later in this video I'll explain the long version. So the short version is you go to this table, which is from the lecture slides, and they give you the common. It's also in the standards, sorry, but they give you the common scenarios basically, and it's been justified in the standards that these numbers are acceptable. They're maybe a bit conservative, but they are accurate they're accurate enough to do our calculations. So, all right, basically, for case 1, okay, we have, it looks like this basically, right? So we have a PFC on the left, and then we have a equal angle on the right, okay? So we're concerned about this equal angle, right? So we're viewing it from the perspective of this equal angle. And so we read this table from here, okay? So this covers 2 scenarios. One, if it's an unequal angle connected by a short leg, or an unequal angle connected by a long leg, or an equal angle, okay? So what does that mean? So remember that an equal angle, which is what we have, right? That's an EA. Just means that both the legs, that's one leg, that's another leg, are the same length, okay? But sometimes you might want to use an unequal angle, okay? So now this is an unequal angle, where one of the legs is longer, right? So that's, that means it's connected, what I've drawn here means it's connected by the short leg. But you can also connect by the long leg like that, okay? So that's also an unequal angle. But we have an equal angle. So basically, KT is 0.85. But now we consider the PFC. So from the perspective of PFC, okay, because we'll need this for later. Where do we look on the table? We look here, right? The PFC connected by the web only. Remember, this is the web of the PFC. Okay, so basically in both our cases, KT is 0.85, right? Okay, I'll give you the full explanation for this towards the end of the video, but yeah, I'll tell you where this comes from. The TLDR is it's from shear lag and eccentricity. Okay. If you have no idea what that is, I'll explain at the end. All right. So let's check the first member, which we'll just we'll just consider the equal angle of the first member. That's the one on the right, okay? So if you consider what I've highlighted in blue, right, that's the cross-sectional area, the gross area. Now we have to reduce our gross area by the bolt holes. So the bolt holes are literally circles, right? But if you think about it, they're actually cylinders, okay? They're cylinders because they pass through our hole. And the section that we're considering basically looks like this if we're drawing it in perspective view. And so we care about this rectangle, right? That is caused by the bolt. So 18 is our hole diameter, right? So 18 is this way, right? The other thing we care about is the thickness of our section, I guess. So the thickness of the leg is 16. So that is going this way. Okay, so that's why we needed that data from earlier. It might have seemed a bit random why we grabbed these, but it's to determine the net area, which is where we're working towards. Okay, so with that said, now we have enough information to solve for AN. Okay, give me one sec. Okay, so we know that AG was 6,200. The hole diameter is 18 and the thickness was 16. All right, so that gives us 5,624 millimeters. Okay, so that's just failure mode 1, right? That's just if you have unstaggered holes. Now, instead of this cross-sectional view, which is easier to understand for unstaggered holes, for staggered holes, right, which are these ones that involve these zigzags, like failure mode 2 and 3, it's easier to view from this angle, like the longitudinal, I guess the elevation view, I guess you can call it. So let's look at failure mode 2 first, right? So in failure mode 2, we have to basically specify the pitch and the gauge. The pitch is the direction that is in line with the tension force, so in the longitudinal direction, so that's tension, right? So the pitch is going that way, so that's 50, right? Okay, now we have two different diagonals. Let's call them, I'm gonna line it up like this, that one and that one. If you can see, this diagonal and this diagonal, right? All right, so this first one, we'll call it SG1, is 30 mil, as you can see. The second one, SG2, is 60 plus 30, okay? So that's 90. It's getting a little crowded, but yeah, that's 90, right? So we have all our numbers that we need, all right? So we have our gross area, but now if we consider failure mode 2, we have 3 bolt holes now. 1, 2, 3, right? So we put a 3 in front of the amount of holes to subtract. The hole diameter and thickness of the section stays the same. But now we have to basically enter in the pitch and the gauge. What did I say the pitch was again? The pitch was 50. And for, sorry, moving the wrong mouse around. I've got like a 2 PC set up here. And SG1 was 30, SG2 was 90. Okay, and the pitch was the same for both of them. All right, you can also stick around to the end of the video and I'll explain kind of where these formulations come from. Okay, so that gives us 5,780 millimeters squared. Cool. All right, now the last one is where we have 4 bolt holes. So that's failure mode 3, paying attention to the purple. So here we have, we basically have 2 diagonals, 1, 2, but they have the same pitch, which is 50, and they have the same gauge, which is 30 for both. So it's only 30 here, and it's only 30 here, okay? But we also have 4 bolts, right? So let's keep that in mind. This time we do 4 for the number of bolts, and for the gauge, we do 30, and we do 30. You can also, if you'd like, do that instead of writing this out twice. Up to you. Okay, and that gives us 5,714 millimeters squared. Cool. Okay, so basically we have to look at these three failure modes and figure out which one governs. So basically the less cross-section there is the one that's going to break first. So if you look at these numbers and compare them, you'll see that failure mode 1 governs. It's the smallest. Okay, so that's the value we're gonna do. Oh, sorry, I keep moving the wrong mouse. I'm gonna move this mouse over here so I don't touch it. Okay, sorry, that's 5,624. I'm doing that in the wrong color. I'm not used to writing in white. This is really weird. That's 5,624. And KT is 0.85, as we discussed before from the lecture slides. And FU is 480. All right, cool. And that gives us 1,950.4 kilonewtons. Happy days. All right, cool. So that's just member 1, right? So we just checked the equal angle. Now we have to do it for member 2, which is the 380 PFC. I feel like my mouse is not in a good spot. Okay. So the gross area is different for this, right? It's 7,030. So I'm just going to write that in for all of these, right? The hole size stays the same because if you remember, the hole penetrates the entire way through, right? Well, now we're only considering the portion of the hole that cuts through one of the members at a time, but yeah, the diameter of the hole stays the same. Okay, so yeah, we have to note down that the thickness for the PFC is only 10, whereas before it was 16, if you recall. Okay, so that gives us 6,670. Far out, I'm not used to these colors at all. 6,670. Okay. Yeah, you do a similar thing, and you'll start to notice that the gauges and the pitches are the same because these two members are attached in the same way. They'll have the same bolt arrangement and the same failure modes and like stagger patterns and things like that, right? Right, this one's 6,767, haha. And then this one is, yeah, we chuck in 10 for the thickness, and this one is 6,726. Okay, so looking at these numbers, the smallest one is still failure mode 1, right? So that's the smallest. Right. Okay, so we can plug that in, and we get that. And keep in mind the PFC also had a KT of 0.85, and we get 2,313.2. All right, so where's this all going? Basically, if we get all of these values from, from before, let me just highlight to you where everything came from. So here are the yield failure capacities, right? And those slot in here and here, right? I'll do that in purple. All right, and then the fast fracture values were here and here, which slots in here and here, basically, right? So if you look at this little tree diagram thing, you have to check what the minimum tensile capacity is for everything to do with the equal angle and everything to do with the PFC. And then breaking it up further, you have to basically figure out the yield and the fast fracture capacity for all of them. And the fast fracture capacity in our case had 3 failure modes, right? So you had to check. You don't have to like work out the capacity for all of those failure modes, but you got to check what the minimum AN is, right? And then yeah, you work it out for that one. The minimum one's going to govern, right? I hope that makes sense. Let's see how this plays out. So, sorry, I'm doing a lot at once here. All right, basically, we look at the smallest number, and that is the fast fracture on the 200 by 200 by 16 equal angle, right? And so we plug that in, and we get 1950.4, and then we apply our capacity reduction factor of 0.9, and we get 1755.4 kilonewtons. Right, that's case 1 done. Cool. Now I want you to try case 2 yourself and see if you get the same numbers. Oh, sorry, the correct numbers, because these are from old workshop solutions. Just keep in mind that on the right hand side here, we have a plate, right, and the exact same equal angle as we were dealing with before, and the plate sits behind here on the left. Actually, I shouldn't draw it like that. It's rectangular, but this dashed line would indicate that it's behind, right? And so, yeah, once you check it, basically the plate will have a different value for Fy and Fu. Okay, and because it also has a different grade and a different thickness. Okay, so basically you're going to find that what happens is the equal angle still governs, right? And there's only 2 failure modes rather than 3, because if you can see here, we have the unstaggered holes and the staggered holes. But the staggered holes can only touch 3 bolts. It can break like that, or it might break like that, but they're not gonna go like in random directions, you know what I mean? They're gonna do the path of least resistance. Okay, so yeah, you'll find that it's actually the exact same capacity as before, because we're still going off of the 200 by 200 by 16 equal angle, which was part of case 1 too, and that's the thing that governs. So you'll find that the force required in case 1 and 2 are the same. Okay, that's the end of the question, but let's talk about the staggered hole and where this thing comes from. It's the additional area that you get back from a zigzag, right? So if you think about it, basically we have the section, and a hole would reduce the section's area, right? So AN is equal to the section minus the whole area. That makes sense. But when you go diagonally, like in a staggered hole, like this, you get this diagonal, right? And that actually adds area. Okay. So basically researchers have found that this is the formula which determines how much additional area that you get. Okay, so it's from this dude. So if you look in the commentary for the standards, right, they tell you that the work done by this guy, Cochrane, in 1922, is basically based on riveted members subject to tension, but it carries over to bolted members essentially as well. And AI just gives you like a quick summary, whatever. You can give that a read if you like. If you want to do the deep dive yourself, look for this dude's paper. But basically, if you compare it, right? So if you just go back to the example that we were doing before, we can look at this diagonal, right? Kind of this shallow diagonal, I guess you can call it. And we can look at this longer diagonal too, and compare the numbers that you would get from using the dude's formula, right? You can color code this, right? So these are the values. And you can compare it from basically like a geometric point of view, right? So that's what I did here. Now, where this comes from is this is adding a diagonal from Pythagoras and then subtracting the straight part, okay? So looking at this triangle here, looking at that triangle there, for example, would be like, this is 30, right? And let's call this h for hypotenuse, right? So hypotenuse, I forgot to mention, this is 50. Hypotenuse is square root of 50 squared plus 30 squared, right? Yeah. But if you think about it, this red part, you have to basically add that, but then also subtract this vertical part out again, right? So you actually have to do minus 30 so that you don't like double count, if you know what I mean. So that's how I got that. And then basically we also have a thickness going that way. So our thickness was 16 mil, I think. So you do h times thickness, which was, that's all that. Thickness was 16, and then you get whatever. So that's what I did here, right? It's here and here. And you can basically see that the numbers are comparable, but they're a little different, right? So if you do it just based on geometry, you'll probably give the section too much AN. The AN will be too big and it will be unconservative. So this is the conservative kind of like area that you get back from those diagonals, essentially. Okay. Next is shear lag, which I want to talk about because I didn't talk about it properly in the first week. But essentially, right, we have KT, which is for fast fracture, and there's that table, if you remember. Let me find it. This one. And you're like, okay, that's all well and good, but like, why is it KT is equal to 1 sometimes, and why is it not 1 in other situations, like here and here, right? When I was doing this course, the way that I understood it was symmetrical shapes give 1, right? Or if it's balanced on both sides of, so say for example, you have 3 members, like that, right? You have tension going here and on that side. So this might be tension T, this might be half the tension on both these smaller members, but the center line, I guess you can say, is like through the middle here, right? And like the whole thing's balanced, right? And so it would be essentially a KT of 1, right? That's one way you can think about it. And that's essentially the concept of eccentricity. I'll write in what? Eccentricity. So eccentricity is another way of saying offset, right? From the middle of something. Yeah, that's offset, right? But these ones are what you call concentric, which means in the middle, right? And if it's concentric, you can say there's 1, right? But that doesn't always apply, essentially, because of a phenomenon called shear lag. So that's kind of what this one is, and it's actually easier to see from what they said in the commentary. Because these are two slightly different things, eccentricity and shear lag. So eccentricity is that thing that I talked about, where you might have like an equal angle and a plate, like how they're drawn here. But where the tension force is going might be a bit offset. So like it might be there or something, for example. The pulling force, the net pulling force. Yeah, well, it has to travel through a medium, I guess. So it might be like, yeah, anyway, whatever. But essentially it's not concentric. What this commentary says is if it's an end connection, right? So imagine this is like a fixed support. Okay, imagine like a tension hanger. Right, tension hanger, it's like a fixed support, and then something's pulling down on it like that. So that's an end connection there. That there's an end connection, and that is where you have the uniform stress distribution, right? And same with this scenario here, but basically, but basically, if it's offset, you get the eccentricity effect, and then you have to apply the correction factor, KT, which will be less than 1. Less than 1 if it's eccentric. Okay, the next thing is shear lag. So the easiest way to think about shear lag is through a drawing like this, right, where it takes some time for, not time, that's not the right word. Essentially, there's parts of your member which are stressed, which is done in red here in this drawing, and there's parts that aren't stressed, and so that like imbalance, if you're thinking of this like have you seen like a finite element model where it's got all the rainbow colors and stuff? If you think of it like a finite element model and the stress distribution, basically it'd be more stressed in these regions and it'll be less stressed over here, and yeah, this is being pulled in tension, and because of that, you have to correct for it. It's going to have a less than 1 KT, basically. So those are the two kind of effects going on, the shear lag effect and the eccentricity effect. Okay. Alright, so that concludes this video. I'll also film another one for compression, but yeah, I hope this explains that.